Okay, so without further ado, let's start our class for today. All right, so today we're going to look at this module one. Okay, in this module one, okay, we're going to learn about the embedded computer. So here, okay, we're going to look at the definition of the embedded system and the difference between the embedded system and the computer system. And at the same time, we're going to look at the characteristic of each of the embedded system. Right, so here first, let's look at the definition behind computer. So what is a computer? So computer is actually an electronic device, okay, for used for store the data and to process the data, typically in a binary form. Okay, every time you're going to do a data processing, do a data storage, okay, that data will be processed or will be stored using a binary number. What is a binary number? 0101. Okay, so that is the definition of the computer, which is okay one device that is used to store data and at the same time to do a data processing. Right, so this is the basic function of computers. Okay, we have four basic functions of computer. First, data processing, then followed by the data storage, data movement, and control. Okay, by looking at these figures here, so here you can see this is a control mechanism. Control mechanism is at the center of, okay, from all of these four components, control mechanism located at the very center. Okay, which is this control mechanism is used to control the data movement, okay, or to control the data process. Either the data is coming from the CPU or the data is going out from the CPU, or sometimes we call it as a processor, right? So then we have the data movement. Okay, so the data movement, which is you're going to move the data either from the CPU to the memory, or you're going to move the data from memory to the CPU. And data storage facility. So the data storage facility is used to store the data. Okay, so whenever you're going to store the data, we will put it inside of this data storage facility. Most of the time, okay, the data storage facility such as a memory. Okay, and last but not least, we have the data processing facility. So this data processing is used to process the data. Okay, the example of data processing such as arithmetics, okay, which is you're going to do the addition, the subtraction, okay, multiplication of that data, or you're going to do logical processing, okay, from that data, or sometimes you're going to do a data rotation, okay, which is we're going to rotate the data to the left, or data shifting to the left, data shifting to the right. So that one will under the data processing. Okay, then whenever the word microprocessor, or sometimes we call it as a processor, is mentioned, okay, most of us will think of the desktop computer. All right, either it is a PC or laptop, because every time you say that, okay, what is the processor of your PC? Okay, the processor of the PC is maybe from the Intel processor, or maybe from the AMD processor, or maybe from the Apple processor. Okay, and for the smartphone, okay, maybe sometimes, okay, when you say the microprocessor, okay, say that, okay, that microprocessor belong to, you can relate it with a smartphone, okay, which is for the smartphone, every time you ask, okay, what is the processor inside a smartphone, okay, so the processor inside the smartphone, you can give an answer such as, okay, maybe the processor is from the Exynos processor, or sometimes you can say Snapdragon processor, or sometimes you can say Apple processor, or ARM processor. Okay, that is for the smartphone. But okay, in this course, okay, we will look at another type of computing system, okay, which is a more common, it's far more common than you ever imagine. Okay, which is, okay, if you look at these devices, you will not you will surprise. Okay, this device is actually belong to a computing system or a microprocessor, right? So this is the classification of the computers. Okay, we can classify the computer into five types. Okay, the first one is a server. Okay, so this server is a computer or a computer program, okay, that manage access to a centralized resource or service in a network. Okay, it's very big. Okay, the server is very big, and of course, it's a very expensive and must available 24/7. Okay, if one of the server is offline, so what happens every time you going to connect to that server? Okay, so you will give a offline error, right? Then we have the desktop. Okay, so desktop is a computer on your desk lah. So this one here, mostly the desktop, okay, you can see in the office or in the laboratories and so forth. Okay, previously, this desktop is very popular lah amongst home users, okay, among office, in the office, okay, but now it will be replaced, it already been replaced by the laptop, okay. So laptop is computer that we use nowadays, okay, which is you can carry on your back and it's very mobile lah, okay, you can carry from one point to another point without any problem. Compared to the desktop is very big, okay, it's a very hard to move, okay, from one point to another point. Okay, so that's why today's, okay, people are using a laptops, okay, to do their daily works, right? And then next, the fourth one, okay, we is classified as a personal digital assistant, okay, which is such as a PDA, tabs, as well as a smartphone. So this is the the fourth type of the computers, okay, which is a computer that we can carry in our pocket, especially on smartphone, because the smartphone is very small. PDA also small. Okay, you can put it inside of your pocket and you can carry anywhere and everywhere. And last but not least, another computer called embedded system, which is a computer that don't look like a computer. Okay, you look at that embedded system, you will surprise. Okay, is it a computer or not? Okay, you will ask yourself, is this device belong to computer or not? Okay, surprisingly, okay, that device is belong to a computer system. For examples of one of the embedded system that close to you is calculator. Okay, so calculator is classified under the embedded system. Okay, and is one of the computer system. All right, so now we're going to look at the embedded system. Okay, what is the definition of the embedded system? So embedded system is actually a computer system. Okay, it's one of the computer system with a dedicated function. Okay, it have dedicated function within a larger mechanical or electrical system, and it is not designed to be programmed by the end user in the same way that a PC is. Okay, so there are two key points that you need to look at here, okay, regarding the definition of the embedded system. One is used to control a function or a range of functions. Okay, so it has a limited function. Okay, embedded system have a limited function and not designed to be reprogrammed. Okay, means that you cannot reprogram the embedded system. Okay, so every time you see that embedded system, okay, the device, okay, it have a limited function, maybe one, two, or three functions, and then you cannot reprogram. Means the meaning behind the reprogram means that you cannot add another features to that device. So that is a definition of embedded system. Okay, and these are the example of the embedded system inside of one car. So in one car, there are a lot of embedded system that is combined together to make a one complete system. For example, okay, for the convenience and comfort, okay, we have the LED lighting. Okay, so you have the LED lighting that is replaced with the previously we have the bulb lighting. lighting system, okay, which is not that good lah. Okay, so now we have the LEDs lighting, and then to control the climate and air condition. So that is one of the embedded system, okay, which is you can control the temperature of your air condition, and to control the air blow, okay, from your air conditions. Okay, either you going to make it uh, faster or lower. Okay, then we have the rain sensitive wiper. Okay, which is this is another embedded system lah, which is used to detect. Okay, it will start wiping the windscreen once it detects a water on the windscreen. Okay, then we have the electric window. So this is another embedded system. Okay, this electric window is used to open and close the window. Previously, we use the mechanical parts here. Okay, which is you roll up and roll down to open and close the window. Okay, now we need to only press one button, and the window will go up and go down easily, right? And then in terms of the safety, okay, there is one embedded system, we call it as an airbag. Okay, so airbag system is one of the embedded system lah inside of the car. So it's used for the safety reason. Okay, every time the car accidents, okay, put into a collision, so what happens? The airbag will be deployed to protect the passenger inside of this car. Okay, then maybe we have some of the car have the occupant detection, okay, which is to detect, okay, is there any passenger inside of this car? So this is very useful, okay, to detect if the baby is inside the car, okay, because nowadays, okay, we keep got a news saying that, okay, baby dies in the car, okay, due to the parents, okay, forgot they have a baby inside of the car, okay. So this occupant detection is very useful lah, okay, to detect if there is any passenger inside of the car, okay, by using a certain sensors lah, such as maybe a movement sensor to detect any movement inside of the car, or you can use the sound sensors, okay, to detect is there any sound inside of the car, okay, because the baby kid will cry lah, okay, if there is no people around, or the car becoming hot, okay, the baby will cry, and it will, once the detection happens, and it will send a notification. Okay, and then maybe we have the direct TPMS. Okay, so TPMS for the tire pressure monitoring system. Okay, is very useful lah to check whether your tire is underinflated or not. Okay, you have got enough air pressure or not inside of the tire. Okay, if the air pressure below the certain threshold, then after that it will pop up a alarm, or it pop up a signal saying that, okay, your tire below pressure, okay, then you need to re-inflate your tire. Okay, so that's why it's under for the safety lah. Okay, for the safety system, okay, we have a few embedded system here. Okay, for the braking, we have ABS, automatic braking system, which is used to help us brake. Okay, help us do the braking. Okay, while the car is driving. Okay, and then for the for the driver assistant, okay, we have the adaptive headlight. Okay, so this adaptive headlight is very useful lah. Okay, whenever, okay, to sense, okay, is there is a car in front or not. If the car is in front, then it will lower the beam. If no car in front, then it will put the light into high beam. Okay, something like that, right? Okay, so inside of the car, there is a lot of embedded system. Okay, so in our house also, we have a lot of embedded system in our house, such as televisions. Okay, you have the blender, washing machines, okay, microwave. Okay, what else? We have the refrigerators. So all of this is actually considered as an embedded system. Okay, because in embedded system, okay, the very definition of the embedded system says that, okay, that device is only dedicated to do a certain function, and it cannot be reprogrammed. Right, so now, okay, we're going to look at the characteristic of the embedded system. Okay, we have a few characteristics here. Okay, the first one is a dedicated functionality. So embedded system is designed to handle only one specific function or one or two, three functions, right? So the system is optimized in terms of hardware and software to ensure it performs its intended task efficiently and reliably. All right. So examples here. Okay, we have a washing machine controller. So this washing machine controller is embedded with a microcontroller that will manage a washing cycle. Okay, because it's a washing machine. Okay, we need to manage. Okay, how many cycle per washings? Okay, how many cycle for uh, ring? How many cycle for to spin to dry or to spin the clothes, okay, to make it dry, right? So this microcontroller will manage lah, okay, the washing cycles and the water level detection, okay, to check, okay, whether what is the water level if you put a load inside of uh, the washing machine, okay, to to make sure that you not waste any water consumption. Okay, and then the spin speed. Okay, you can control the speed of the spin. Okay, by put by controlling the RPM. Okay, maybe if the fabrics is uh, very hard fabric, okay, heavy fabric. Okay, you can put the RPM to highest numbers. Okay, so that it can spin uh, very fast. Okay, if you have a fabric that need to have uh, very what we call here the easy care fabrics. Okay, so you need to make sure that okay the speed is reduced. Okay, and then the timer control lah to okay to control the time of the washing. Okay, other than that, other examples of the dedicated functionality such as a digital thermostat, okay, which is designed only to measure and control the temperature. Okay, you cannot use the digital thermostat to do any other things except to control and to measure the temperature. Okay, similar to washing machine lah. Okay, this washing machine only dedicated to manage the washing cycle, to check the water level, to do this, to set the spin speed and timer control. This washing machine cannot do word processing, for example, cannot send SMS, for example. Okay, because it already have the specific function. Similar to your calculator. Okay, the calculator, what is the function of the calculator? To calculate, okay, to do a calculation. Okay, and that calculator cannot be used to send text or to send SMS or to make any call. Okay, so that is what means by the first characteristic here, which is a dedicated functionality. All right, so the second one here is a real-time operations. Okay, many embedded systems are designed to respond within a strict time frames. Okay, making them a real-time system. Okay, so in the real-time operations, they can be classified into three real-time. Okay, the first one is a hard real-time system. Okay, which is failure to meet the deadline. Okay, will result in a system failure. Okay, so example of the hard real-time systems such as a airbag deployment in a cars. So if the system detects a collision, okay, the airbag control system must trigger deployment within a millisecond to prevent any injury. Okay, what happens if the airbag is got a delay? Okay, the airbag is not trigger promptly. Okay, what happens? So it will it will inject the passenger. So that is what we call as a hard real time. Okay, failure to meet a deadline will result in a system failure and will cause the total catastrophic to user. Okay, to the end user. And then the second one, we call it as a soft real-time system, okay, which is it defined as a delay may reduce the performance, but do not cause to a total failure. Okay, even though it have a slightly delay, okay, uh, it only reduce the performance, but not result in total failure. And firm real-time system is an occasional deadline miss are acceptable, but the output is discarded if it is late. Okay, another example. Okay, example for the soft real-time system such as a streaming video player. Okay, so a video streaming device must buffer and display the video smoothly. Okay, for example here, okay, you are watching a live broadcasting, okay, to watch the football match. Okay, even though you got delay, okay, in terms of the streaming, okay, your neighbor, okay, maybe your neighbor, the streaming is on time, but yours got 5 second delay, but it is still acceptable. Okay, as long as it can display the video smoothly, right? So that's what we call it as a soft real time, because the consequence behind it, after if the what we call here, if if the failure to meet the deadlines, okay, it not cause a total failure to that system. All right, another examples here is, okay, maybe you are online gamer. Okay, you play on online games. Okay, so a delay in response may cause a lag, okay, affecting the player experience, but not crashing the game. Okay, the game still go on, but only the player experience is, it only affect the player experience. Okay, and last but not least is the example for the firm real time. Okay, which is an online reservation system. So if a reservation is delayed and another customer book the slot first, okay, the system must discard the request. Okay, for examples, okay, you're going to buy a, a flight ticket. Okay, you browse to the airline punya ticketing. Okay, and then suddenly, okay, you pick the slot, and then it asks you to, okay, proceed for the payment. Okay, you wait for some time, take your time. Okay, so what happens when there is another person, okay, which is buy the same seat, okay, as you on the same time, but you still not proceeding with the payment, so that seat will already be taken by that person. Okay, so that one is belong to a firm real time. Right, so this is the second characteristic of the embedded system lah. Okay, the third characteristic of the embedded system is a resource constraint. Okay, the embedded system often designed to operate with minimal resources, okay, such as a limited RAM, CPU power, and storage. Why is that? Okay, because uh, embedded system only have a dedicated function. Okay, so to run this dedicated function, you no need to have a very powerful device, okay, very powerful processor. So we just use a minimal resource so that it can operate the whole system. So this will ensure that the system is cost effective, okay, because you have a limited RAM, okay, the CPU power is not that high, okay, so the cost will be reduced, okay, compared to if you use the very high or powerful CPU, okay, and it also have an energy efficient and compact, right? So examples here, digital thermometer, all right, so since again the digital thermometer is used to measure the temperature. Okay, so it only require a small microcontroller such as the Arduino Uno, for example, a small LED screen, and a minimal RAM to display the temperature readings. Okay, no need to have a very big RAM. Okay, because you're only going to display the temperature. Okay, you did not do anything. Okay, except to display the temperature. Okay, so unlike a PC, okay, this thermometer, okay, does not require large memory or high processing power. Okay, and the four characteristic is a highly reliable and stable. So embedded systems are designed for a long-term stability and minimal failure rates. Okay, so it must, okay, many operate in a critical application where failure can be catastrophic. Okay, so we need to have a very high reliable and stable device. Okay, so for example here, traffic light controller system. Okay, so traffic light controller system is one of the embedded system. Okay, which is it must operate 24/7 without failure. All right, so it is to ensure the smooth traffic flow and safety. So what happens if the traffic light control system is not working that day? So you, okay, so it will cause a heavy traffic jam because, okay, the car stops at that junction, right? So you need to have a very high reliable and stable, okay, for every embedded system that you design. And number five is a power efficiency. Okay, so embedded systems are battery operated, so it requires low power consumption. Okay, because most of the time, an embedded system is battery operated. So when use a battery operated to make the battery last longer, okay, you need to have a low power consumption, right? So how to make sure that, okay, that device or that embedded system have a low power consumption, okay, you can use a power optimization technique to extend the battery life. Okay, example of the power optimization techniques such as support low power sleep modes. Okay, whenever the device is not used, okay, you can put the device on in the sleep mode, right? So when you're going to use the device, okay, then after that you wake up the device, okay, from the sleep. Okay, or you can adjust the voltage and clock frequency of the processor based on the workload. Okay, so by adjusting the voltage and clock frequency, and you can reduce the power consumption. And last but not least, this is what the STM32 do. Okay, the ARM processor do. They disable unused peripheral clocks. Okay, so the peripheral that you're not using, okay, you disable that. Okay, the DPIO that you not use, okay, you just disable that one to reduce the power consumption. Okay, examples here is a smartwatch lah. Okay, smartwatch designed to operate for days or week on a small battery and uses low power microcontrollers such as ARM Cortex-M to optimize the power consumption. Okay, that is a characteristic number five. Okay, now we're going to look at the last characteristic of for each of an embedded system is must have a compact, small size, and cost effective. Okay, we should have a low cost because they are designed for a specific task rather than general purpose computing. Okay, since they have their function have limited functions, okay, and it must have a very need to have a low cost lah. Why? Because we only use a minimal resources, and then the size must be small enough. Okay, so it can be achieved by optimize the hardware components, okay, to reduce the size and manufacturing cost. For example, here, okay, we take a digital cameras. Okay, so since the digital camera, okay, you need to bring it, okay, along with you to carry it with you. So you need to make sure that the digital camera is not that bulky and not that heavy. Okay, so it's so that easy for you to carry from one point to another point. So how to do it? Okay, design with a small microcontroller. Okay, you need to have a small microcontroller, a small image sensor, and a display to fit in a compact enclosure. Okay, make sure that all the display sensors and microcontroller is small enough. Okay, and even though this microcontroller is small, but okay, that microcontroller must have a high performance, such as the ARM processor. Okay, because you're going to do the image processing, okay, you need to have a very high performance microprocessor. But to make sure, since the digital camera is a battery operated, it's okay to you need to reduce the power consumption. How to do it? By using a microcontroller, the high performance microcontroller with a low power consumption. Contohnya, okay, you can use the ARM processor. Most of it is a have a low power consumption. Why? Because the ARM processor uh, use uh, a method which is they disable all the clocks that are not used. Okay, only the GPIO use are enabled. Okay, so this is how one way to reduce the power consumption. Okay, and here is the difference lah. Okay, between the general purpose computer, okay, such as the PCs, okay, laptops, and the embedded system. All right, first, general purpose computers intended to run a fully general set of applications. All right, but embedded system run a few applications often known as a design type. Contohnya, calculator. Okay, so normal calculator, okay, only have a few applications that you need to do, which is to calculate the normal arithmetic such as plus, minus, divide, and multiply. Okay, and if you're going to do other arithmetic such as sine, tan, binary conversion, integration, etc., then you need to buy a scientific calculator, which is have a few functions, okay, compared to a normal calculator. Okay, and then the general purpose computer is an end user programmable. Okay, so what is an end user programmable? You can reprogram your computer. Okay, so that you can run another function. Contoh, I give you a contoh. Okay, if you're going to watch a movie on a computer, so what you need to do? Okay, you just install a video media player, okay, to play a movie. Or if you're going to listen to a song, okay, so what you need to do? Okay, you can install the Spotify to your what we call to your computer. Then after that, you can listen to a song. Okay, if you're going to playing games on your computer, so what you need to do? Okay, you can install your games on that computer. After it's installing process is finished, then after that you can play the games. Right? So while embedded system, okay, that end user programmable. You cannot reprogram that embedded system. If the calculator says that okay, it's only used to do a normal arithmetic calculation, tambah tolak bahagi darab. Okay, so it only does tambah tolak bahagi darab. Cannot do the binary conversion. Cannot do a integration or logs unless you buy another computer, another calculator, such as a scientific calculator to do that function. All right, and then for the general purpose computer, fastest is always better. Okay, so compared to embedded system, the embedded system is operate in a fixed time constraint. Okay, which is we have a minimal resources as long as the device is working. So that should be more than enough lah. All right. So additional performance may not be useful or valuable. Okay, if you increase the performance, okay, if you use the higher C processor, for example, high RAM, what happen? Okay, it will only cost you more money. Okay, and that device will be more expensive. So that's why embedded system will only use the minimal number of resources compared to the computer. Why? Because computer faster is always better. Okay. For example, if you open your window, all right, and then your window can straight away, okay, from starting to uh, pop up the whole window screen only take you 5 seconds. Then you happy lah because your computer is very fast. Okay, what happens if you start your computer by pressing the on button and then you need to wait for 5 minutes, okay, to wait the window, okay, to start booting. So what happens? It's frustrating, right? Okay, so for the general purpose computer, faster is always better. All right, and the last one here is how to differentiate the differentiate feature, how to differentiate between one computer and another computer by looking at the speed. Okay, some computer got this speed, some computer have this speed. Contoh, computer A have a 2 GB of processor, computer B only have 1 GB of processor. Okay, and then you can differentiate the feature by look at the software compatibility. Okay, the software might can be installed on the computer A but cannot be installed on the computer B. Contohnya, if you're using iOS, okay, some of the iOS program cannot be used inside of the Windows OS. Okay, there is a software compatibility. And the cost. Okay, you can differentiate the computer by looking at the cost. Of course lah. Okay, the computer that have a high performance, high processor, high RAM, okay, will cost you more money compared to if you have a low spec computer with a low RAM, okay, low processor speed, okay, it will much cheaper. Okay, what about the embedded system? How to differentiate between the one embedded system to another embedded system? Okay, first one we look at the power consumption. Okay, for example, you have we look at the calculator. We have a lot of calculator out there. Okay, one calculator is a battery operated. The other calculator is battery operated and solar powered. Okay, so that is how you going to differentiate between one embedded system and another embedded system. And then the cost, okay, the cost for calculator. Okay, some calculator, the cost, it costs you only 5 ringgit. But the other calculator do the same function, tambah tolak bahagi darab, but it costs you 10 ringgit. Okay, so it depends on this is how to differentiate lah. Since both use to do a normal arithmetic, tambah tolak bahagi darab, but the cost from one calculator to another calculator is different. All right, and the size. Okay, there is a small calculator, there is a bigger calculator. Okay, so the size also is used to differentiate between one embedded system and another embedded system. Right. So that is for the characteristic of embedded system. Any question up until here? That's all I thought from you guys. Okay, before we go to the embedded system design. Okay, if no question, then we go to this embedded system design. Right. So what we have in the embedded system design. Right. So the embedded system design process involves a multiple stage. Okay, starting from the specification, okay, to the final testing here. Okay, so now we're going to look at what are the activities involved inside of this stage. Okay, we have 5 stages here. All right, first is a specification, then followed by the architecture, hardware and software design. After that, we integrate the system, and last but not least, we do the testing. Okay, so the specification phase defined as the functional and non-functional requirement of the embedded system, which is it includes the system functionality, which is you're going to identify. Okay, what are the problem statement and user needs? Okay, how to you're going to make the system function based on the problem statement that you identified earlier. Okay, then the performance constraints. Okay, so you need to define, okay, what are the hardware and software constraints for the system that you're going to design. The power consumption, okay, is it the device need to be battery operated, or is it the power is coming from the power outlet? Okay, if it's battery operated, so how you going to reduce the power consumption? Okay, and then cost and size limitations. So you need to identify that. Okay, what is the cost? Okay, what is the acceptable size for that device? Right, and last but not least is to identify the communication protocol. Okay, such as if, okay, are we going to use the serial communication, or are we going to use the parallel communication? Okay, for the serial communication, okay, are we going to use the UART or USART communication, or is it as SPI communication? Just something like that. This is under the specification, okay, which is you define all the functional and non-functional requirements. Okay, the second stage is architecture. So this architecture piece, okay, define the hardware, software partitioning, and system component. So it includes, okay, now we already define what is the needs. Okay, now we're going to identify, okay, what are the architecture behind of the system. Okay, so the architecture is such as choose the microcontroller. Okay, are we going to use a microcontroller or a microprocessor? Okay, what is the difference between microcontroller and microprocessor? Okay, so microcontroller means that the microcontroller unit means that all of the the components needed to make a one complete computer system is already been there inside of one single chip. For example, what is the components needed to make a computer system? Okay, we need to have the processor, we need to have the input-output devices, and we need to have a memory. These three things needed, okay, in order to make a one complete computer system. Okay, for the microcontroller, all of these components already been inside of one single chip. But for the microprocessor, okay, microprocessor unit, okay, the microprocessor unit only consists of the processor, only consists of the CPU. So you need to buy the memories, okay, another chip for the memory, another chip for the GPIO to make one complete system. Okay, and then here under the architecture, we're going to select the operating system. Are we going to use the operating system or not? Okay, are we going to use the real-time operating system or a bare metal? Bare metal means that there is no operating system inside of that device. Okay, while RTOS, okay, we need to have a operating system so that that device will works. Next is identify, okay, the memory. Okay, what is the suitable memory? Okay, what is the RAM size? What is the ROM size? Okay, the power management. What are the power management techniques that we need to use in order to limit the power consumption? Okay, to reduce the power consumption, and how to do the I/O interfaces. Okay, so this is where you're going to do in this architecture piece, right? Once finished, okay, once we already identified the processor that we're going to use, okay, and then the operating systems, the RAM size, okay, the ROM size, how many GPIO, okay, that we're going to use. Then after that, we go to the design process, okay, step number 3. So the design phase involves the creating the circuit schematic, okay, the PCB layout, and software architecture. Okay, on the design here, okay, we can divide it into hardware design and software design. Okay, so the engineer from the hardware will design all the hardware here. The engineer from the software will design of the programs, okay, for the system to work. Okay, so the hardware and software engineer will work independently. Okay, the hardware will do all the hardware part, and while software engineer will do all the software part. Okay, and then once they are finished, hardware and software already finished, then after that we need to integrate them together. Okay, we need to integrate the hardware and software. Okay, which is now we are on this phase here, system integration. Okay, so in this phase, okay, will integrate the hardware, software. Okay, if you have sensor, you're going to integrate the sensor communication module into a complete system. So it is ensure all the component works together seamlessly. Okay, so here, so these are the activities that is under the system integration, which is the hardware software integration to make sure that the software properly control the hardware peripherals. Okay, and then you can do the communication testing. Okay, to validate. Okay, this protocol, the communication protocol that you're going to use. Either you're going to use the SPI, UI, or wireless connections, and you're going to do a power consumption and which is to measure the power efficiency under different workloads. Okay, you put the small load. Okay, what is the power consumption? You put the you increase the load. Okay, then you're going to look at what is the power consumption. From there, you can see the patterns. Okay, you analyze. Okay, if the power consumption is not that high between the high load and low load, okay, so it should be good enough lah. If there is a margin, okay, the difference is very high, then you need to reduce do a power optimization to reduce it. Sorry. And the last phase here is the testing. Okay, so the testing phase ensure that the embedded system meet functional performance and reliability requirement, such as unit testing. Okay, which is here you're going to test the sensor accuracy, okay, the response time of the sensors, okay, and then the power consumptions, right? Integration testing, so this one will be done under the hardware software integration. Okay, and then we do the system testing, okay, to look at the overall system behavior, and then the stress testing, okay, which is the operating in extreme condition. Okay, you put a very heavy condition, extreme conditions, and see whether your system, okay, can accommodate, can work under that extreme conditions, right? So that is for the embedded system design. Okay, now you're going to look at the design matrix. Okay, so the design matrix, what is a design matrix? Okay, the design matrix are measurable characteristics that determines, okay, the efficiency, performance, and quality of the embedded system. So this is how you're going to measure lah. Okay, the efficiency of the design, the performance of the design, okay, for each of the embedded system. Okay, and this matrix, okay, the design matrix will guide the engineer in designing, optimizing, and evaluating embedded system. So design matrix is very important, lah. Okay, so to make sure that your design is good, all right. So if your design is not good, then you can do some optimization, okay, to make your design is in a good and your design it at optimum level. Okay, first we can look at the performance. Okay, we can measure the performance. Right, the performance. What is the performance that we're going to look at? The speed at which the system execute its task. Okay, so here are the performance that you can check. Okay, from your design. First is a response time. Okay, which is a time taken by the system to respond to an external event. Okay, if the event occur. Okay, so how fast your system can respond to that event. Contohnya, okay, uh, you have you design a system. Okay, we see this system here is used to check the water level. Okay, you have a sensors you put on okay, on inside of the tank, okay, and this sensor here to check the water level. Okay, if the water is passed through the sensors, okay, the sensor should detect that water immediately. So that is the response time. Okay, if the sensor is got delay detecting the water, so what happened here? The response time will got delay lah. Okay, so then the execution time, okay, the time is required to complete a specific task. Okay, so if you have a one task, okay, what are the time, okay, to finish that task? Okay, that what we call as a execution time. And last but not least is the throughput, okay, which is a number of tasks processed per unit time. So if you can process multiple tasks at per unit time, means that your uh, system is good lah. Okay, because it can do multitasking. Okay, that is in terms of the performance. And then now we're going to look at the power consumption. Okay, the power consumption is the amount of power required to operate the system, which is crucial for the battery powered device. Okay, so here you can check lah. Okay, what is the power consumption? Okay, you can check the voltage, you can check the current flow, and you can check the voltage of that your device. Okay, and then cost, okay, which is the total expense of designing, manufacturing, and maintaining the system. Okay, so this is another design metric that you can measure, which is development cost. Okay, the hardware, software testing cost. Okay, this is under the development cost lah. Okay, whenever you design the system, okay, you're going to look at okay what are the cost for each of this system. Okay, that is under the development cost. Production cost, okay, the cost per unit for the mass manufacturing. Okay, so if you're going to produce many devices, many device, okay, what is the production cost? Okay, how much it costs? Okay, for the mass manufacture. Okay, and then maintenance cost. Okay, a long-term software hardware updates. So these are under the cost, and then we have the reliability. Okay, which is this reliability can be measured by the ability of the system to function correctly over time without failure. Okay, if that system can function properly, correctly, so that system we call it as is a reliable system. Okay, in terms of the flexibility and scalability, okay, which is the ability of the system to adapt to a change in the requirement or integrate with a future technology. Okay, which is can the system be updated easily? Okay, if not, cannot update easily, so the system is not flexible lah. Okay, and in terms of the scalability, can it support future expansion? Okay, let's say lah you design a system, okay, and then in the future, okay, you're going to put a more sensor to that system. Is your system able to adapt to it to support the future expansion? If yes, then okay, the system is under this scalability, okay, which is it can support the future expansion. Okay, last and not least is a safety and security. So this is a protection against hardware failures, cyber threat, and unauthorized access. So for example here, how to measure from the safety, okay, to ensure that the system does not cause any harm. Okay, so make sure that your system have very high safety. Okay, will not cause harm to the end user. Okay, in terms of the security, okay, it can be measured by protect the system from hacking. Okay, especially in the IoT home security. Okay, if your system is easy to be hacked, what happens? The security is low lah. Okay, so to make sure that you have a high security, so that it is not easy to be hacked. All right, so that is for the module one. Okay, the module one is actually about the embedded system, the introduction